Today we are going to address important reduction reaction with respect to alkenes, alkynes and aromatic hydrocarbon. Let's first start with catalytic hydrogenation of alkenes, which usually takes place in the presence of hydrogen gas that is adsorbed on a metal surface. There are two phenomena. One is known as adsorption and another is known as absorption. Adsorption basically reflects a physical phenomena. In other words, we can say that the hydrogen gas is temporarily adsorbed on the metal surface. So when hydrogen along with the metal is exposed to react with a double bonded compound, hydrogen gas ate across the double bond in a thin fashion. In other words, we can say that the hydrogen molecule ate to the double bond from the same side. So basically hydrogenation is prompted or accelerated by a metal catalyst such as platinum, palladium or nickel. Here I have shown a device which is known as power hydrogenation apparatus, which is employed for hydrogenation of alkene. Again, alkene, when hydrogenation takes place, it can either be heterogeneous or homogeneous. Hydrogenation is basically a reduction phenomena. Why? Because during this process hydrogen is added. So whenever there is addition of hydrogen, it reflects a reduction phenomena. So hydrogenation can either be homogeneous or it is heterogeneous. When both the reactant and the catalyst are in the same phase, such as a gas, a liquid or solid, then we call it a homogeneous catalysis. And as far as the heterogeneous catalysis is concerned, that reflects the presence of catalyst and a substrate in a different medium or different phases. As we have studied catalytic hydrogenation of alkene, so it reflects an example of heterogeneous catalysis. Why? Because the catalyst, hydrogenation and alkene, they are in different phases, not in the same phase. Here the demonstration is showing some important feature of catalytic hydrogenation of alkenes. Here the platinum catalyst has shown, in which hydrogen gas has adsorbed. So whenever alkene molecule come to contact with a metal catalyst, the hydrogen molecule break off and two hydrogen atom adds to a double bond. By this way alkene is reduced to alkanes. Similarly, homogeneous catalysis such as the Wilkinson catalysis is very important in organic synthesis. Usually this catalyst is used for synthesis of chiral material or when we require to transform a achiral starting material into a chiral material which is optically active. Such hydrogenation is known as such reaction are known as enantioselective synthesis or asymmetric induction. This is an important hydrogenation catalyst, especially Wilkinson catalyst is important hydrogenation catalyst which was employed by two scientists, Ryoji Nayori and William Knowles, that won 2001 Nobel Prize in Chemistry for their catalyzed hydrogenation reaction. Now let us focus on addition reaction of alkynes or hydrogenation of alkynes. Hydrogenation of alkyne is a bit different as compared to hydrogenation of alkene, in a sense that we can partially reduce alkynes to alkene. When we complete the process of oxidation, reduction, then the alkynes can be transformed into alkanes rather than alkene. So whenever we stop the hydrogenation or reduction of alkynes at alkene stage, then we can use a modified catalyst that could stop the reaction at alkene stage. So So just here on the screen, the table reflecting the three different chemical bondings, such as for example carbon single, double, and triple bond, and total energy associated with each type of bond has already shown. So just like catalytic hydrogenation of alkenes, the catalytic hydrogenation of alkyne is also uh, facilitated with the help of a metal catalyst. We have two different type of hydrogenation or reduction reaction with respect to alkynes. The difference is categorized by addition or the fashion of addition of hydrogen across a triple bond. Whether the hydrogen addition is taking place from the same side or it is from the opposite side. If hydrogen molecule add across a triple bond in a thin fashion, as we have studied in catalytic hydrogenation of alkenes, then such reduction reaction is executed with the help of a Lindlar catalyst. These catalysts have important feature of giving us an cis alkenes. So Lindlar catalyst is basically hydrogen adsorbs on the surface of palladium and barium sulfate solution or mixture. This reagent is inactivated by the use of quinoline and methanol. We poison it, the catalyst, in order to reduce its reactivity. Uh, why we are reducing its reactivity? Because we want to stop the reduction of alkene alkyne at alkene stage rather than proceeding the reaction further towards alkane. So that's why we poison it. So Lindlar catalyst is used for getting cis alkenes, or in other words, reduction of alkyne is done with the help of Lindlar catalyst to get a cis alkene. Contrary to cis alkene, we can also reduce alkynes to transalkene as well, but for this purpose we need to use another important catalyst or another important reduction reaction, which is known as metal ammonia reduction. Here on the screen I have shown a metal ammonia reduction, in which first of all the alkyne is reacted only those alkynes which are terminal. In other words, those alkynes which are internal. Here the alkyne those alkyne in which the triple bond is not linked with any hydrogen, known as internal alkyne. So when internal alkyne as shown on the screen is made to react with sodium in liquid ammonia, it gives rise to formation of a transalkene rather than cis alkene. Ammonia is used in this reaction. The boiling point for ammonia is minus 33 degrees centigrade, which is at room temperature. When sodium is react with ammonia, it gives rise to formation of a blue solution, which is due to electron that has given by sodium to a solution. The reaction is very important. If we focus on the mechanism of metal ammonia reduction, then it entails or it gives insight how alkyne are transformed into a cis or a trans alkene. Basically, in metal ammonia reduction, we get a trans alkene rather than cis alkene, because in this case there is no syn addition but hydrogen to hydrogen atom across the triple bond in anti manner. Just focus on the mechanism. It involves some simple steps. The first step involves the addition of electron across the triple bond, and that give a radical anion. We call it radical anion because it has a radical as well as the anion portion as well. So that's why it called it a radical anion. The second step involves the addition, or you can say abstraction, of hydrogen from ammonia by the radical anion for giving a vinyl radical. Here the vinyl radical is important to understand with respect to its stability. If both alkyl group are on the same side of the vinyl radical, it will be unstable. But if the two group are on the opposite side as it has shown on the screen, then it will be stable. So that's why we get this vinyl radical for the sake of getting stability. Just look at mechanism step number 3, in which the most stable trans vinyl radical has obtained. And ultimately in the step number 3, another electron adds to a vinyl radical for giving a vinyl N9, and this vinyl N9 ultimately abstract another hydrogen from ammonia molecule for giving a transalkene rather than cisalkene. So we get alkene with anti-stereochemistry in sodium ammonium metal reduction.